there is one other technique that's important to be able to do, and that is to use MATLAB to find by hand inverse transforms. And this is easiest to explain entirely with examples. Let's say we have 6s plus 14 all over s squared plus 4s plus 3. The command that you're going to use returns three variables: r, which is the technical word for residue, but it means what the numerators would be; p, those are the denominators, the poles; and k. K is what is left over if you do the if you've got an improper fraction and you need to divide. The command is called residue, and it takes two vectors. The first vector are the numbers in the numerator, so the coefficients are 6 and 14, and then it takes the coefficients in the denominator, so that's 1, 4, and 3. Okay, for this particular problem, it will spit out an r vector. Remember, that's the numerator values of 2 and 4. It'll spit out a pole vector. Remember, that's the denominator values of -3 and -1. And because this is a proper fraction, it doesn't need to divide, and so the k vector will be empty. Now, these numbers correspond to 2 over s plus 3, because the first pole is -3, plus 4, your second numerator, over s plus 1, corresponding to the -1 of the pole, and that's it. And so now, armed with this, you can directly do your inverse Laplace transform. You can see it. It's 2 times e to the -3t plus 4 times e to the minus t, and the whole thing times the u of t. Okay, so it makes things much easier. How does it handle problems in which you've got a non-zero k? How does it handle improper fractions? If the fractions are improper, and this is clearly very improper, then your r vector for this will be 4, 8. Your pole vector, denominators will be -3 and -1 again. But your k vector now will not be empty. In fact, it'll have two numbers, because you would have had two coefficients if you divided through. And that corresponds to s plus 2. So these are your k. That's your k vector of 1 and 2. S plus 2 plus, and everything else is the same. It's 4 over s plus 3. That's your first part. And then your second part is 8 over s plus 1, your second part. And now you can directly transform this. So just by inspection, you could have transformed this to 2 e to the minus 3t plus 4 e to the minus t, all times u of t. And that's your answer for the first one. You could also transform this into, this first guy is the derivative of an impulse. The second one is 2 times an impulse. And then the last two are just different types of decaying exponentials. And all of this is times our u of t. You might wonder, hey, why isn't the u of t multiplied by this too? It shouldn't be multiplied by this because this doesn't need it. These are not left-sided functions. These won't blow up to infinity for time less than 0. In fact, these things are 0 everywhere except for t equals 0, whereas you need the u of t here because these guys will blow up to infinity for t less than 0. So you've got to stop that. Okay, last problem is, how do we handle having complex roots? So now our numerators will be complex conjugates. And our denominators, our poles, will also be complex conjugates. So if one is -3 plus j2, notice how even MATLAB has the first number always with opposite signs. The next will have to be its conjugate. This is a proper fraction, so for this our k will again be empty. And this corresponds to our first number being j3, which we could write in polar notation again as 3 at an angle of 90 degrees. And it corresponds to having an alpha of +3 and an omega of 2. And if it's not clear that +3 came from here and the 2 came from here. And so again, armed with this, you could now write its transform and say it's always going to be equal to 2 times the magnitude of a, e to the minus alpha t cosine of omega t plus theta. So this would be 2 times 3, e to the minus 3t cosine of 2t plus 90 degrees, or 6 e to the minus 3t cosine of 2t plus 90 degrees, and that's our inverse transform. Now, if you wanted to be really tricky, you could do some neat trigonometric things. Since this is 90 degrees, you know this is going to look like a sine of something, but as engineers, we like to keep it as cosine. And that's how you use MATLAB to help you break apart a polynomial ratio in S to find the inverse Laplace transform.